Welcome back to the Deep Dive.
Great to be here.
And a really big hello today to everyone listening at Ishik Boys High School.
Yeah, especially Mr. Jager's physics class.
Absolutely. We hear you've been digging into some really interesting stuff, and we thought we'd do a deep dive today that connects right into your lessons. Hopefully, it reinforces things and maybe even shows them in a new light.
Definitely.
So have you ever, stood by the ocean, maybe seen a huge cargo ship, massive thing, weighs thousands of tons, and it just floats like it's nothing?
Yeah, it's pretty amazing when you stop to think about it.
And then you can take a tiny little pebble, drop it in a pond, and poof, sinks right to the bottom.
Absolutely.
How does that work?
Yeah.
It seems counterintuitive, right?
It does.
Well, today we're diving into the world of fluids and a really cool concept called buoyant force. We're going to try and unpack why some things float, why others sink, and how liquids and gases, their properties, play this, huge role.
And what's really neat is how these ideas pop up everywhere, not just ships and pebbles.
Oh, absolutely. These aren't just textbook theories.
Nope, real world stuff. From breathing to, I don't know, hot air balloons, physics is kind of quietly running the show.
Okay, so let's start simple. Usually when we talk about matter, we say solid, liquid, or gas, right?
The three main states, yeah.
And a lot of the time when we talk forces, motion, things like that, we focus on solids. You know, things with a definite shape, a block, a ball.
Things that don't really change shape easily.
Exactly. But think about pouring a glass of water, or even just the air in the room right now. What do liquids and gases have in common that, say, the chair you're sitting on doesn't?
Well, they can flow. That's the big one.
Yeah.
And they change their shape. They take the shape of their container.
Perfect. That's the key difference. Their ability to flow and alter their shape. And any material that can do that, we call it a fluid. Simple as that.
So liquids and gases are both fluids?
Yep. But a solid, like a brick, nope. It keeps its own shape, doesn't flow, not a fluid.
Got it.
Now, even though they're both fluids, liquids and gases aren't exactly the same. There are important differences.
Right.
Take liquids first. They have a definite volume, but not a definite shape.
Okay. What does that mean exactly?
Well, imagine you've got, say, a gallon of gasoline. You pour it from its can into your lawnmower tank.
Right.
The gasoline, the liquid, changes shape. It fits the tank perfectly now.
But,
and this is the important part, you still have exactly 1 gallon. Its volume hasn't changed.
Okay. Like pouring water from a tall, skinny glass into a wide bowl.
Yeah.
Same amount of water, just spread out differently.
Exactly. The volume is fixed. Now, gases,
They're different.
totally different. They're like the free spirits. They have neither a definite volume nor a definite shape.
Okay.
So if you take some gas from a small container and put it in a much bigger one, it doesn't just change shape, it spreads out completely, fills the entire new container.
Doesn't just sit at the bottom or anything?
Nope. It expands to fill whatever space it's given. Its volume isn't fixed at all.
That makes sense. Like if you spray air freshener,
Good example.
you spray it in one corner, but eventually you smell it everywhere in the room.
Because the gas just expands and fills the whole volume.
Right. It's pretty wild how we just live with these different behaviors every day and don't always think about the physics behind it.
Totally. Okay, so fluids flow, they take shapes, but what about how much stuff is packed into them?
You mean like how crowded it is?
Yeah, exactly. Like if you've ever been crammed into a really busy elevator,
Oh yeah, not fun.
you might say, wow, the density of people in here is way too high, right?
Yeah, you might.
Well, in physics, density is basically that. It's a measure of how much there is of something in a given amount of space.
Oh,
And for fluids specifically, we usually talk about mass density, which is just the mass of the substance divided by its volume.
mass per unit volume.
Exactly. And you'll often see it written with the Greek letter rho, looks kind of like a curvy P.
Got it.
And the standard unit we use, kilograms per cubic meter? KilogMO.
Kilograms per cubic meter.
Right.
So whenever we say density from now on, we mean mass density.
Yeah. For this deep dive, density means mass density. Now, there's another important thing about density, especially comparing liquids and gases. It's compressibility.
Ah, right. How much you can squeeze them.
Yeah, I used to think you could just squish anything if you pushed hard enough. But that's not really true, is it?
Not at all. It's a really key difference. Solids and liquids, they're almost incompressible.
Incompressible, meaning...
Meaning you could apply a lot of pressure, but their volume, and therefore their density, barely changes at all. Think about water. Its density is about 1,000 kg/day.
It's stable.
Very stable. Or an iron, much denser, around 710 to 860 kg/day. But again, you can't really squeeze a block of iron or a bottle of water into a significantly smaller space.
Okay, so solids and liquids hold their density pretty well.
But gases are a whole different story. They are compressible, very compressible.
Meaning their density can change.
Oh, absolutely. Change the temperature, change the pressure, and the density of gas can change a lot. That's why when you see density values for gases like air is about 1.29 kilojoule meters, hydrogen is way less, like 0.09 kilojoule meter of air. Those numbers are always for specific conditions, standard temperature and pressure, usually.
Ah, okay, so gas density isn't as fixed. That's important.
Hugely important. It connects back to why some things float in air, like balloons, and others don't.
Right. Which brings us back to our big question, that giant ship floating, how, and think about this too, have you ever noticed how things feel lighter when they're underwater?
Oh yeah, like trying to lift a big rock out of a river, easier when it's submerged.
Or even just lifting a friend in a swimming pool. Seems way easier than on land.
Definitely. Feels like you've got superpowers.
That superpower, that upward push you feel from the water,
Yep.
that's it. That's buoyant force.
Right?
It's this upward force that any fluid, liquid, or gas exerts on an object that's submerged in it, even just partially submerged.
So the water's literally pushing up on the object.
Exactly. Think about lying on an air mattress in a pool. What's holding you up?
The buoyant force.
The buoyant force, pushing up on the mattress, and you.
And because that force pushes up against gravity pulling down.
Right. It makes things seem lighter. We call that their apparent weight.
Apparent weight. So it's not their actual weight, but what they seem to weigh in the fluid.
Precisely. Even something heavy, like a brick that definitely sinks, it still has some buoyant force pushing up on it in the water, so its apparent weight in the water is less than its actual weight in the air.
The buoyant force just isn't strong enough to make it float in that case.
Exactly. Which leads us to one of the most famous stories in science, Archimedes.
Ah, the Eureka guy.
The Eureka guy. The legend goes he was a brilliant Greek mathematician, right? And the king gave him a tricky job.
The crown problem.
The crown problem. The king had this fancy new crown, supposedly pure gold, but he suspected the goldsmith might have cheated, mixed in some cheaper silver.
But how to prove it without melting the crown down?
That was the challenge. So Archimedes is thinking about this, thinking. And then he gets into his bathtub.
And notices their water level rise.
And overflow. And suddenly, bam! It hits him.
Eureka.
Eureka! I found it. He supposedly ran through the streets, well, you know the story. But what did he find?
He figured out the connection between the displaced water and the buoyant force.
Exactly. Let's picture it. You have a bucket, full to the brim with water, maybe with a little spout right at the top.
Okay.
Now you carefully lower, say, that brick into the water. What happens?
Water overflows, comes out the spout.
Right. And you collect that overflow water in another little container, that's the displaced fluid. And here's the genius insight. The volume of that water you collected, it's exactly equal to the volume of the part of the brick that's under the water.
Ah, so the space the brick takes up underwater is filled by the displaced water.
Precisely. And this led him to Archimedes' principle. Any object, whether it's completely underwater or just partially submerged, experiences an upward buoyant force. And the magnitude, the size of that force, is equal to the weight of the fluid that the object displaced.
Wow, so the buoyant force isn't just some random push, it's directly related to the weight of the water or fluid that got pushed out of the way.
Exactly. That's why it's easier to lift your friend in the pool. They displace a certain volume of water, that water has weight, and that weight is the buoyant force helping you lift.
Okay, that makes sense. It's like the water itself is helping push them up.
You got it. And in terms of a formula, we say FB, the buoyant force,
Equals the weight of the displaced fluid. FG, displaced fluid.
or FB equals MF times G, where MF is the mass of that fluid you displaced.
Okay, so that principle is the foundation for understanding floating.
Absolutely. Now we can connect it back. Why does the huge steel ship float, but the tiny pebble sink? It's all about balancing forces.
Right, weight pulling down, buoyant force pushing up.
For something that's floating peacefully, like that cargo raft on the lake we mentioned, those forces are perfectly balanced.
In equilibrium.
Exactly. The upward buoyant force is exactly equal to the object's total weight pulling down. The net force is zero. It just sits there.
Which means if you know something is floating and you know its weight.
You automatically know the buoyant force. It has to be the same magnitude, just pointing up.
That's handy.
So for that ship, it floats because the buoyant force pushing up on its huge underwater hull is equal to the ship's enormous weight. But how can that be if it's made of steel, which is way denser than water?
Ah, but the ship isn't a solid block of steel, is it?
No, that's the trick. It's mostly hollow inside, filled with air.
Right. If it were solid steel, it'd sink like, well, like a lump of steel. But by shaping it into a hull, you create this massive volume.
A huge space that pushes aside or displaces a tremendous amount of water.
And even though the steel itself is heavy, all that air inside is super light. So the average density of the whole ship, the steel plus all the air inside its volume, ends up being less than the density of the water.
Average density, that's the key concept. It's not just the material, but how it's structured.
And if the average density is less than the fluid's density, it floats.
Ingenious. And this isn't just for ships. Nature figured this out too. Think about a fish.
The swim bladder.
Exactly. That little internal balloon. How does a fish just hang out at a certain depth or rise or sink?
It adjusts the gas in the swim bladder.
Yep. It can inflate it, maybe by gulping air or taking gas from its blood.
Yeah.
That increases its overall volume without really increasing its mass much.
So its average density goes down, less than water.
And it rises to sink.
It deflates the bladder, lets gas out. Average density increases.
And down it goes. It's controlling its buoyancy by changing its average density.
And submarines do basically the same thing, just, engineered.
Right, with those big ballast tanks.
Pump water in to increase average density and dive.
Or pump compressed air in to push the water out, decrease average density, and rise to the surface.
And if they get the balance just right, matching their average density to the water's density.
They achieve neutral buoyancy, just hovering there, suspended. Pretty cool.
Very cool.
So, to sum up the conditions, if an object's average density is greater than the fluid's density, like our pebble, or maybe that raft after it gets a hole and fills with water,
then its weight is greater than the maximum buoyant force it can generate. The net force is downwards.
and it sinks,
But if the object's average density is less than the fluid's density,
like the ship or a piece of wood,
then the buoyant force, when fully submerged, is greater than its weight. Net force is upwards.
so it rises to the surface and floats partially submerged until the buoyant force exactly balances its weight again.
Perfect balance. And the neutral buoyancy case is when the densities are exactly equal. Just floats wherever you put it underwater.
Right. Now here's an amazing example of buoyancy happening inside you right now. Your brain.
My brain is buoyant.
Kinda. Your brain sits inside your skull, but it's not just rattling around, it's floating in cerebrospinal fluid.
Okay.
And that fluid has a density about 1,007 kilodrometer. Your brain tissue itself is slightly denser, maybe around a 10 and 40 kilodrometer.
That's nearly the same density, but the brain is a tiny bit denser.
Exactly. But because it's immersed in a fluid that's almost as dense, there's a huge buoyant force supporting it.
So the fluid is holding most of the brain's weight up.
Pretty much. Your brain weighs about 1.4 kilos, but because of buoyancy, its effective weight, the weight supported by your neck and skull base, is maybe less than 100 grams.
Wow. That's incredible.
Isn't it? It protects your brain, cushions it from shocks when you move your head. It's a natural shock absorber system, all thanks to buoyancy.
Physics protecting our brains. I like it.
Me too. Okay, ready to apply this? Let's try a problem like something you might actually see in class. Back to Archimedes and that crown.
The suspected fake gold crown. Let's do it.
So imagine this bargain hunter finds this crown, looks like gold, feels heavy.
Okay.
She takes it home, gets out a scale. In the air, the crown weighs 7.84 newtons. That's its actual weight, FT.
7.84 newtons.
Got it. Then she gets a container of water, suspends the crown completely submerged in the water, and weighs it again. Now the scale reads only 6.86 newtons.
Ah, its apparent weight.
Got it.
Less because of buoyancy.
Exactly. Apparent weight is 6.86 N. The question is, based on these measurements, is the crown pure gold?
All right. Classic density detective work. How do we start?
Well, we need the crown's density to compare it to gold's known density, and Archimedes helps us here. What's the first thing we can figure out from those two weight measurements?
The buoyant force. It's the difference between the actual weight in air and the apparent weight in water.
Right, so FB, weight in air, apparent weight in water,
That's 7.84 N minus 6.86 N.
which equals 0.98 newtons. That's the upward buoyant force from the water.
Okay, FB is 0.98 N. Now what? We need the crown's density.
Remember, Archimedes' principle also tells us the buoyant force equals the weight of the fluid displaced.
Right. FB, weight of displaced water.
And there's this super useful ratio that comes from the principle. The object's density divided by the fluid's density equals the object's weight in air divided by the buoyant force.
Ah, okay. So object density, fluid density. weight in air buoyant force that connects everything.
Exactly. We know the fluid is water, and its density is pretty much 1.000109 kg/MMR.
We know the weight in air, 7.84 N, and we just found the buoyant force, 0.98 N.
So we can rearrange that ratio to solve for the crown's density.
Ground density, water density, weight in air buoyant force.
Plug in the numbers. Crown density, 1.00 times 10 millkg/MMR, 7.84 N, 0.98 NN.
Let's see, 7.84 divided by 0.98 is exactly 8.
So the crown's density is 8 times 1.00 and 10 milligmopars.
Which is 8.010 kg/MK. That's the calculated density of the crown material.
Okay, moment of truth. Is that the density of gold? We need to check our references.
Looking up pure gold, its density is 19.3 at 10 kg/MK.
Wow. Okay, so our crown is 8.0810, and most gold is 19.3 to 10 milliliters.
Not even close.
Not even close. That crown is definitely not pure gold. Our bargain hunter maybe got, well, a bargain price, but not on gold. Probably some kind of brass or bronze, maybe.
Could be, but the physics tells us for sure it's not gold.
And just like that, understanding fluids, density, and buoyancy lets us solve mysteries, test materials, design ships, submarines, even understand our own brains.
It really does connect to so much.
So just to quickly recap our dive today, we defined fluids, liquids, and gases that flow.
Distinguish between them based on definite volume and shape.
We tackled mass, density, how much stuff in a space, and saw how compressibility differs between liquid solids and gases.
Introduce buoyant force, that upward push from fluids.
And unpack the big one, Archimedes' principle, buoyant force equals the weight of the displaced fluid.
Which then explained floating and sinking based on comparing the object's average density to the fluid's density.
Using examples from ships and fish to submarines and even brains.
It's all density and buoyancy. Now, here's something for you all to think about. Linking back to density and buoyancy, especially with gases.
Oh, a challenge question.
Yeah. Why do hot air balloonists typically use helium, which is really light, instead of just using, say, pure oxygen, heated up really hot? Both would be hot gases. Why helium specifically? Think about density.
Ooh, good one. Mull that over, maybe chat about it with your classmates or Mr. Jaeger.
Definitely.
Okay, that's all for this deep dive. Remember, everyone, stay in contact with your physics teacher. Stay creative.